In this video, we will introduce something called the substitution property, which is going to be one of our go-to methods of integration. So the substitution property is going to be an integration technique that I'm going to claim undoes the chain rule. So essentially, if we want to evaluate an antiderivative of the form given here, and notice this looks kind of like something we would get from the chain rule. What I'm thinking about in the back of my mind is that if I differentiate, let's say, big F of g of x, and I'm going to go ahead and let big F be an antiderivative of little f. Then what the chain rule is going to give us is big F prime of g of x times g prime x, which is really f of g of x times g prime x. So if we were to anti-differentiate the little f g of x times g prime of x, what we would really get back is this. That is, combining together these two sides, the antiderivative of f g of x times g prime of x is going to be the big F, an antiderivative of little f, evaluated at that inside function, g of x. Now, to give it a more procedural aspect, what we're going to do is think that if we take the substitution, we're going to let u be g of x. So the g of x becomes a u. Then thinking in terms of differentials, which we've previously discussed, du is g prime x dx. So the g prime x dx becomes a du. And the idea is that if you use this technique, you start with what might look like a difficult integral, and it becomes simpler looking. You evaluate this simpler integral, and then you resubstitute. A very important observation here is that when you're using a substitution, you start off with your first integral only involving that variable x, and your second integral only involves the variable u. There's no middle ground here. We can't mix the x's and the u's. We go from all x's to all u's. We evaluate, and then we resubstitute. And we'll see precisely here in a moment what I mean by the resubstitute. So let's go ahead and put this technique to work for us. So when we apply this technique of substitution, and let me kind of remind you of what we had. The integral of f of g of x times g prime of x equals the antiderivative of f of u du, where here u, the substitution, is g of x. Kind of the indicator to try using a substitution for us is it's going to be something that we can evaluate with our previous techniques. And here this square root of x plus 1 is really throwing us off. Or you look for kind of this inside function g and its derivative, so a function derivative pair that you're seeing in your integrand. So in this example, this is something that we just cannot handle with our previous methods. And I see the inside function x plus 1. By inside, I mean it's in the square root. So what I'm going to do is let u be x plus 1. Then in terms of differentials, du would be the derivative of x plus 1, which is 1, times the differential dx. And I want to use these to rewrite the integral solely in terms of u's. So we have the antiderivative of the square root of x plus 1 dx. X plus 1 we said is u, and dx is du. So we can go from solely the variable x to solely the variable u. And this integral in terms of the variable u is much simpler for us to evaluate because the square root of u is really u to the 1/2. So we just undo the power rule. 1/2 plus 1 is 3/2. So we have 1 over 3/2, or 2/3 u to the 3/2 plus c. And note where we are at this point. We've started off with the integral that was difficult for us to evaluate. We've used a substitution, and it resulted in a simpler integral. we evaluate, and then we resubstitute. That is, the original question was phrased in terms of the variable x, so our answer needs to be in terms of the variable x. And we go back to our substitution. Note, u is equal to x plus 1. So each u becomes an x plus 1. And this step of the problem is what we refer to as the resubstitution. So let's look at a similar example. So we're going to take the example we had on the previous slide and we're going to modify it slightly. We're going to include this extra x. So note, as we observed before, because of the square root of the quantity x plus 1, we don't have any previous method that allows us to handle this antiderivative. So we're going to try a substitution again. And the thing to pick for u is something inside another function, and x plus 1 is inside the square root. Du is dx. So if we look at our integral, I'm going to rewrite it, x times the square root of x plus 1. So just like the previous example, x plus 1 under the square root becomes u. The dx becomes du. And note, we need to go from an integral only involving the variable x to an integral only involving the variable u. So that means everything inside our entire integrand here needs to be written in terms of u. And we have a leftover x. And whenever you have a leftover x, you simply go back to your substitution. Your substitution gives you the relationship between u and x. So in this case, we see that x, if you isolate it, is u minus 1. So this remaining x becomes u minus 1. So written solely in terms of u's, we have u minus 1 multiplied by the square root of u. So I'm going to make that u to the 1/2 du. And now this is a much simpler example for us to evaluate because we can distribute through. It's the antiderivative of u to the 3/2 minus u to the 1/2. And we can take care of each term individually. So 3/2 plus 1 is 5/2. So we get 2/5 u to the 5/2. 1/2 plus 1 is 3/2. So 1 over 3/2 or 2/3 u to the 3/2 plus c. And whenever we evaluate an indefinite integral with a substitution, our last step is going to be this resubstitution. So we need to take each of the u's that we see and replace it with the x plus 1 that we substituted above. So this becomes 2/5 x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus c. And this is the value of our indefinite integral.